Hello. In the previous video, I explained how we use the p-value in to make the decision. It's the same idea I introduced in the last lecture. And let's think more about the significance level alpha. How does it affect? When you even if you change alpha, as I said, it does not affect the p-value because it's like p-value is calculated independently and then compared with alpha. So change in alpha does not affect the p-value itself. However, of course, it affects the decision. So remember, the null hypothesis is rejected if p-value is smaller than alpha, right? Rejected smaller than alpha. Then if you increase alpha, that means you are increasing the hurdle, you are increasing the bar. So increase in alpha means you are going to reject more. So your rejections will happen more frequently, and you are less generous toward the null hypothesis. You are a little more strict than before. So toward the null hypothesis. For example, so if your null hypothesis is rejected at 5%, that means so it doesn't like the rejection may happen based on other decision rules like t-statistic or critical values. But anyhow, if you calculate the p-value from this data, the p-value must be smaller than 5% if the calculation was correct. If the decision was correct, its p-value must be smaller than 5%. That means even if you increase the significance level of 5% to 10%, it will be smaller than 10%, right? So it shows the relationship between the significance level and the frequency of rejections, right? So if you reject at alpha, then all the higher significance levels will reject the null hypothesis too. And vice versa, if H0 is not rejected at 5%, which means p-value is greater than 5%, so any significance level smaller than 5% cannot reject this p-value because p-value is already greater than 5%. So you can go the other way. However, so if H0 is rejected at 5%, I don't know if it will be rejected or not at 1%. Because what it tells you is only that p-value is smaller than 5%. But I cannot say if it's smaller than 1% or greater than 1%. So I don't know what will happen when you change the significance level to 1%. Similar here. Not rejected at 5%. But when you increase 10%, increase the significance level to 10%, I don't know. You cannot tell, you cannot expect what would happen in that case. Anyhow, it's a simple basic relationship between significance level. The key idea is increase in alpha leads to more rejections. That's the most important idea. And we are going to maybe we are going to use this intuition later in the next lecture. So keep that in mind. And let's go to the second approach. The second approach is the t-statistic method. Actually, the procedure is quite similar. You obtain the t-statistic, which is already used in the p-value. So anyhow, when you calculate the p-value, you have to calculate the t-statistic. So it's just kind of a byproduct of the p-value approach, but it's often understood as another separate method. Also, it has its own interpretation and intuition. Let's think about the decision rule. So t-statistic is this. We are going to interpret this as standardized difference between x bar and mu 0, right? So x bar is what you observe and mu 0 is what you believe. So what you see and what you believe could be different, and standardize the difference so that the scale is always to the standard normal distribution. So the scale of this difference is always comparable to the standard normal distribution, so you can rank and measure how different they are. And given the difference, the decision rule can be assumed this way. So I am going to reject the null hypothesis if the difference is too large. This is the most intuitive decision rule. And mathematically, when I say the difference is large, it is defined in this way. The absolute value is greater than a certain number a. I'm going to discuss how to choose a in the next page. But so this is mathematically how we express too large, right? So remember, t, its absolute value, absolute value of t is greater than a means t itself is greater than a or smaller than minus a. So the difference could be toward the positive side or negative side. So x bar, what you observe, could be greater than what you expected or too small than what you expected. So we include both sides here. And then automatically non-rejection happens. You don't reject when the difference is not that large, small enough, or it's close enough to 0. So t, absolute value of t is smaller than a, which is equivalent to saying that t statistic is in between plus minus a, right? So absolute value is smaller than a is implied by lying between plus minus a. Now, next step is to choose a. How do we choose a here? And we are going to choose a so that this decision rule is equivalent to the p-value, right? Anyhow, we use the same t-statistic for the p-value approach, and we have to make the same decision from the same data. So how can we choose a to make it equivalent to the p-value approach? Let's think about this. So everything starts from the significance level. Significance level is the tuning parameter that adjusts the level where you cut off, how much you accept, how much you reject. And significance level is given by alpha, which is a probability. Alpha is a probability like 1%, 5%, or 10%. And when I say the significance level is 1%, it means I'm going to reject the most 1% suspicious outcomes. That's how I interpreted, how I introduced the significance level in the first lecture of this part. So this means I am going to reject alpha outcomes. Alpha probability outcomes are going to be rejected. And that means when I say total alpha outcomes are rejected, you have to think about two tails. The extreme most suspicious outcomes lie on the right side tail as well as the left side tail. So you have to split alpha into two sides. So I'm going to reject top alpha over 2% and bottom alpha over 2%. That's what it means. Significance level alpha means. Then from now on, we use the same method that we learned in chapter 6. Chapter 6 normal distribution chapter, and chapter 8 confidence interval chapter. So remember, top alpha over 2 probability value was denoted this way. Z value subscript alpha over 2. So this means the probability alpha over 2 is above this value, right? We studied this, how to calculate this in chapter 6. So if you don't remember what we did there, please review the videos. Anyhow, so and we practiced, and as you see from chapter 8, z alpha over 2 is fixed by alpha. So usually when I give you alpha, then you can find it from Microsoft Excel or use the common numbers like 1.96, 1.64, 2.58. there are some like commonly used, like usual suspects. So you may choose from them. So I'm not going to go into the details how we calculate this value. Review the previous videos. Anyhow, this is the threshold, the cutoff level, the cutoff. So you are going to reject H0, the null hypothesis, if the absolute value of t is greater than z alpha over 2, the z value. So if the standardized difference is greater than this or smaller than minus z, then you have to reject. You do not reject the null hypothesis only when the standardized difference is within plus minus z alpha over 2. So in the picture, this is what we are doing. For example, if you choose 5%, 5% means you are going to reject most unlikely outcomes of 5%. How do I say? 5% most unlikely outcomes. Anyhow, you are going to reject 2.5% here and 2.5% here. These guys, the shaded area, is the outcomes with the least likely outcomes. So shaded area is the collection of most unlikely outcomes within top 5%, right? And so top side, on the right side, 2.5%, on the left side, 2.5%. And what you have to find is this value, this A, the value A is top 2.5% value, or 97.5% from the bottom. This is what we did in the earlier chapters. So you have to find it. It is 1.96. We learned how to find it. And now compare the two decision rules. P-value is compared with alpha, and t-statistic is compared with the z-value implied by the significance level. So whenever the significance level is fixed, given for the same significance level, these two decisions must be the same. Especially, you can check it easily by checking that when t-statistic equals to this z alpha over 2, its p-value, so p-value is calculated from the t-statistic, so p-value must equal to alpha. So when this holds with equality, and then the other side will hold with equality. So let's try that. So p-value was calculated this way. Simply, we know the absolute value of t, when the absolute value of t equals z alpha over 2, you can write it this way. And this is exactly what we wanted. So the bottom alpha over 2% and top alpha over 2%. So when you sum, it equals to alpha. So this shows that the two decision rules are equivalent. So no matter what you use, it does not matter. But then why do we use the t-statistic? The major difference between the t-statistic and the p-value is that t-statistic captures the direction. So p-value is only between 0 and 1, 0% to 100%. So even if it's, like say, if it's 5%, I don't know, it does not say whether x bar is too large or too small. But t-statistic tells you if it's minus. When t-statistic is minus, it tells you that your belief is larger than your observation. So you may reduce the belief. Or vice versa, if t is positive, that means the observation is larger than your belief. So you have to update your belief by increasing the number. So that's the main difference between the p-value and the t-statistic, and often the t-statistic itself could say something like, for example, if t is 2, if t equals 2, that means x bar, the observation is 2 standard errors above your belief. So it tells you the degree of the deviations, the differences between the observations and the belief. So t-statistic itself can be of interest. Then you may use the t-statistic. And also it is easier to calculate. than the p-value. So that's why t-statistic is used in some examples, in some cases. And I explained that here. So, and t-statistic, by the way, the required information for t-statistic is the same required information for the p-value, because t-statistic is just an intermediate outcome to calculate the p-value. So you need the same numbers like x bar, standard deviation, and sample size, and the null hypothesis, but you do not need alpha. These properties are shared by the p-value and the t-statistic. And now let's think about alpha. What happens if alpha changes? When you increase alpha, that means you are going to reject the null hypothesis more often. To do that, you have to make the z value smaller. So look at this. The rejection rule goes like this. So to reject h0 more often, you have to make z lower so that t-statistic is easily goes above the z value. Or otherwise, you may understand it this way. h0 is not rejected only when t-statistic is within plus minus z. If you make the interval smaller, then h0, the null hypothesis, is less likely to be not rejected, more likely to be rejected. It's more likely to be outside of the interval, so you are going to reject more. So increase in alpha makes z values smaller, and then the null hypothesis will be more likely to be rejected. That's the same property as the p-value, but the algebra is slightly different. And previously, when alpha increases, there is no intermediate step here, but we have to go through z value as an additional step to be compared with the t-statistic. Okay, in the next video, I'm going to explain the p-value, the critical value approach, the third approach, which is a little bit different from the p-value and the t-statistic.